Thanks. I'm really excited to be here, and I'm really excited to see you guys hanging in here until Thursday. It's a long week, but just out of curiosity, is anyone here interested in invasive plants? Raise your hand. All right, I'm in the right room, so that's really good. So what I want to talk about today is the idea of trying to develop general ecological principles for managing invasive plants. And this fits in well with the EBIPM framework. We're trying to repair processes that we think are damaged. Now, just to give you a little leeway on this, there's two things that are challenging with this. First, when you're trying to develop a synthetic idea, it's really easy for people to poke holes in it, because there's a lot of exceptions to the rules. If you guys have been involved with invasive plants, we can often find more exceptions to our rules than we can find general rules. Okay, so this is a trick that we're kind of dealing with here. So it's a little bit of a tough road to navigate, but I think we're going to be able to make some very valuable headway here. So this is where we are. You guys all understand this fully now, right? So I don't even know. Basically, you've seen this a couple times. This represents the general EBIPM model, which involves a couple key steps. Tony did a nice job sort of walking us through those major steps that are there. The principles fit in here, and I know you guys can't see this, so I want to explicitly spend just a minute or two examining what are we really asking here. So we know the issue here, we often have systems that are in some sort of degraded state. Maybe it's not a monoculture disease, but it's something that we would like to gradually go in a more desired trajectory. Plant communities change through time. Like Tom very clearly developed for us, the conditions that are going to allow us to do this really have to do with addressing the ecological processes that underscore these changes. With invasive plants, we're really talking about repairing damaged ecological processes. So what we often do, we have tools like the rangeland health assessments where we can go out and make some measurements to see what sort of state our initial community is, health-wise, how degraded is it. We look at things like bare ground, rills, community compositions. And this does allow us to make some projections about which processes are probably damaged. And those rangeland assessment tools have been developed for quite some time. As managers and practitioners, then, what we're trying to do within an ecological framework is to use our tools and strategies here that are available to us to try to modify these processes. So that's a pretty reasonable way to look at it. So what we're really trying to do in this talk are to explore the principles that help us guide not only our decision-making process, but importantly, and I think this is really important if we're trying to make on-the-ground changes, is to adjust and hone our expectations for these outcomes, so that our expectations for our management outcomes are clearly aligned with the principles that will influence the outcome of how we apply our tools and strategies. So that's where we're headed. So I bet a very reasonable question that a lot of you guys have on your mind are, do principles exist? And that's a very, very valid question. So probably to talk about this a little bit, we need to first define what an ecological principle might be. And the way I've approached it here is to take the general concepts of principles in, let's say, like a field like physics, and adapt it to ecology. So we simply say that ecological principles are constraints that link ecological processes to the relative abundance of the species we have out there. So it is a general term, but what we're proposing is that there's physical, mathematical, environmental constraints that dictate composition of species on the land. The idea of actually needing to apply principles to ecology in general, restoration ecology, has been around for a while. It's in fact been a long identified need of our field, but there's also been a lot of debate and a lot of questioning of, can we actually do this in restoration ecology? Do principles exist? So based on this, we need to understand, can we move forward? And what I'm going to propose to you is, yes, we can, but we need to move forward in a context that represents how we're actually going to be able to use these principles. So there's a couple points here, and this is a lot of text, but I thought it was helpful to be explicit when we're talking about principles, and we can all kind of get on the same page. So there's three things we need to keep in mind. We need to be able to consider how these concepts that address how the probability of management changes, these are essentially going to be probabilities. Okay, so if our management tools are designed to change a process, it's not a yes or no answer. There's going to be degrees of probability that that management tool will actually work. But to be effective, we're going to have to attach principles that we're going to use to their associated ecological theory and concepts. If you take these things in a combined fashion, we end up talking about the condition in which the principles hold. Okay, and to me this is like the most fundamental point. If we're trying to develop principles of invasive plant management and so forth, we might say, you know what, most weeds grow fast. I bet you guys can think of some weeds that don't grow that fast. So if we're trying to assign principles to these values, we need to understand, where are we grounding this ecological theory and the particular concepts? And so if we even it feels like physics. Physics, when they're making predictions based on their principles, there's certain conditions in which those principles are applicable. It's not that they apply to everything. And this is really, in my mind, which is the key point that is going to allow us to move forward with actually applying principles to invasive plant management. So I really have, the main goal of this talk is to develop that exact point, is that we can, yes we can. So my argument here is, yes, we can develop principles, but to do that and have them be useful, we need to understand the conditions in which those principles hold. Just to illustrate that here, okay, you guys see the ship here, right? So the ship's carrying part of a bridge. So if you were the civil engineer that built the bridge, and your boss came in and said, dude, what did you do? Your bridge collapsed. To the civil engineer, what do you say? Say, well, I didn't design it to have a tanker take it out. Like, all my calculations are based on weight going down and how that's distributed across these beams and these columns, and that's what I did it for. I didn't do it to have some sort of lateral stress applied this way. So, all that text, all that talk, what we're basically trying to do is understand, if we're using like physics as an analogy, so we have principles that we've used to build this bridge of physics. We're not expecting those principles to hold if a tanker goes through it. We're expecting those principles to hold if a car is on top of our bridge. Okay, so this, to me, is really the major dichotomy. And if you're going to remember anything from this, this is what we need to remember. I argue that, yes, principles can be developed and applied if we understand the conditions on what they hold. And that is the trick for us, in an area that we need to spend a lot of time thinking about in our management. So I'm going to go through three just examples of how general principles have been developed, and there's a guide back there where we've summarized some of these, and the associated ecological theory and concepts that actually support the application of these principles. Within each of these, I'm going to talk explicitly about the conditions in which we expect these principles to hold. So the first one is seeding principles. Like in Tom's talk, he had a seeding treatment, and he had a certain outcome. Yeah. A lot of us spend time and money seeding, we know that the outcomes can vary, but we also have some ideas that are fairly intuitive. We have some handle on about some principles of seeding. Basically, we could offer, and most of us find this very digestible, is that increasing our seed sowing density and frequency of desired species will actually increase our desired species density. This isn't earth-shattering. Most of us know if we do increase seeding rate, in most instances we do get more plants. Frequency, we don't really mess with that too much, but maybe it makes sense. We go seed multiple times. Maybe we have a better shot at getting something. There's a couple conditions that limit this principle and how it's going to apply. First, the environmental conditions are going to need to exceed some certain threshold. And we're also going to have to manage invasive species and their priority effects to actually have our seeding treatments be effective. And if you guys haven't, thought about priority effects, it's simply who comes first wins. We know our invasive species come first many, many times. So we need to take away that advantage to actually have our seeding effect be useful. Okay, so I think most of us, we're fairly agreeable to this. Well, how do we come up with these, and how do we understand what's going to go on when we do a seeding treatment? So there's a little bit of math that might help us out. And raise your hand if you're like me and math makes you nervous. Be honest. All right, at least there's a couple of people. So the math makes me nervous. But the thing I really like about math, this is probably a little hard for you guys to see, is it does allow us to make some quantitative predictions about what might be going on. So if you can't see this too well, what we're basically asking is how many sites, which is this N here, is won by species I. And let's say this is a species you seed and you want to get established. Well, according to this equation, there's a couple things that are going to influence us. These are general lottery models that have been around in ecology for quite some time, and they're actually been tested quite well. And we can use these to understand what's going to dictate the outcome of our seeding. And basically, there's a couple of factors here. One, this xi is the number of sites where species I already exist. This beta is how many seeds that species is producing. So this you can change by your seeding rate, of course. And this C is the relative competitive ability of the species. So what we see right here, according to these lottery models, is that as a manager, if we adjust seeding rate and we adjust competitive ability, then we are going to have an impact on a given species. So increasing the seeding rate of our desired species, decreasing the competitive ability with cheatgrass and reduce head by removing those priority effects are going to be helpful. Another important term here is this K, which is part of this product. K is the number of safe sites available. So what it's saying here is that, well, if you seed too much and you seed more seeds than there are a number of safe sites for your seeds to occupy, you're going to get a diminishing return on your seed investment. K, interestingly enough, if we think about it, is going to influence with the environment. Okay, so our environmental conditions become more and more harsh, K is going to decrease. So at some point, there's some environmental threshold that determines K. The last thing, if we consider our frequency of seeding and simply a probability of a seed reaching this site, we can also conclude that if we maybe increase the frequency of our seedings, we may increase the probability of actually finding these sites. So this is one example where we understand some of the ecological conditions and theory that are actually going to determine if this particular principle holds. That makes sense, kind of what we did? We just wanted to take a very common and digestible principle associated with seeding and really look at how these associated processes determine your outcome. So here's a quick example from a study with perennial grasses and an annual grass in California. Here they're looking at sort of a biomass production function on this axis here. And what they did is they either sowed broma seeds at the same time as the perennial grasses, or they delayed broma seeding. So this is manipulating that priority effect. And they had two seeding rates, with the black bars being the higher seeding rates. And we can see pretty easily here that if we take away that competitive effect, so the C in that lottery model, we can have a significant effect on what our seeding actually does. So this is just demonstrating how we would transfer that model to something. So the second thing, this is the second example. We're just going through 3 examples to show you how these principles can be developed and properly applied. Has to do with disturbance. And again, there's several principles that we detail quite thoroughly in the handout here. We're just going through a couple of them here. So this principle here, we might say infrequent and less intense disturbance will favor desired species over invasive. So in Tom's talk, he applied things like mowing and fire, which are disturbance treatments. And now what we're trying to understand is taking that tool and understanding what principles will actually determine the impact of how well that tool works. So when does it work, and how well does it work when it does work? So that's the general principle, but any of you that have played around with fire or targeted grazing or anything, we know that all of these disturbance principles can be severely modified by type, duration, and timing of the disturbance, the spatial extent of the disturbance. So these are modifying conditions that determine when those principles hold. But what I want to do, just like the other example, is show you a little bit of data that allows us to develop support for this general principle. And this is a really, really interesting data set. It's a little hard to take in all at once, but this is from Marcel Monic, 1996, did a really classic study with pines, the genus Pinus. And what they did is say, well, pines are everywhere globally. Some of these pines that have been taken out of their native range have become invasive, which are these black dots here. Some of these pines that have been taken out of their native range have not become invasive, just introduced. We know we have analogies of these in our grass systems too, And so what they did is, instead of looking at native pines versus invasive pines, they looked at pines that have been introduced globally and not spread, and pines that have been introduced globally and they've turned out to be quite invasive. And they looked at the pattern of things like juvenile period, so how long they're actually in a juvenile stage, and how long, what is the interval between seed crops. So how frequently are they producing seeds, and how fast are they maturing. And not unintuitive to us, what we see is these invasive pines, pines that have become invasive, they go through the juvenile period much quicker, and they have a much shorter interval between seed crops. So if we take this idea that invasive species grow faster, they go through the developmental stages faster, and they more frequently are producing seed crops, then we can start thinking about how our disturbance timings, frequencies, and intensities are going to influence that. So then we might develop the principle that, well, if our weeds have very, very short intervals between seed crops, these frequent disturbances are obviously going to favor the invasive species. And if we stretch out that disturbance regime longer, we may start favoring our native species. So the last example here, and I'm going to spend a little bit more time on it, because this is an area that I've been trying to figure out for myself a little bit more about what's going on, and it ends up to be a little bit more complex. And it has to do with the performance of invasive species like our cheatgrass and medusa head in our resource poor rangeland.
Well, 6, okay.
Okay. All right, so we're wrapping things up here. So one of the issues here is we know invasive plants, invasions tend to increase along both fertility gradients and disturbance gradients here. So basically in this graph, darker is more invasive. So we know that as we increase site fertility, invasive plant density increases. So it makes sense to us that in our low fertility rangelands, invasive plants should probably be less abundant. They shouldn't be performing quite as well as their natives. So we know this is not generally true though, so we wanted to examine some of the issues associated with this, and we looked at a series of data, because the data is kind of all over the board about invasive grass performance in low nutrient systems. So the question is, why is Medusa-head and cheatgrass doing so well, even though our soils are so low in nitrogen in a lot of our restorations? So we pulled this data together and did a quantitative analysis here, and I'm going to show you just some data real quick that shows an effect size metric, where we're basically taking the annual grass response here in an actual log form and subtracting it from the perennial grass form. And so with this metric, anytime our metric is above 0, it means the annual grasses win. Anytime it's below 0, the perennial grasses win. If it's at 0, then they're tied. That's all we have to really remember. So we looked across low nitrogen and high nitrogen systems and the performance of annual grasses and our native perennials. We looked at factors like biomass, tillering, and growth rate. And what we found across all these metrics and all these data is that our annual grasses are consistently growing bigger, producing more tillers, and growing faster than our perennials, regardless of soil fertility level. And to us, this is a little bit counterintuitive relative to what some of the ecological theory and principles would predict. We also see the outcomes with competition, where we have both native targets and native perennials and invasive annual grasses growing in different nitrogen environments with either annual grass native, perennial natives. And this is a lot of data to look at, but the basic point is our fertility environments aren't really changing the intensity of competition on a per plant basis. And so one of the ideas here, and I'm just going to wrap this up, is that some of our natives and our invasive plants, they differ in how they're constructing their leaf tissue. Okay, so these are our invasive grasses here: cheatgrass, Medusa-head, ventinata. Cheatgrass has very thin leaves, which means that when they fix carbon, they're making a lot more surface area than our native perennials per unit biomass. And this actually allows them to grow a lot faster. So if you're making very thin leaves, this is going to be sort of your growth trajectory, versus if you are perennials, you're on this trajectory. So in this situation, soil fertility is not going to change the competitive relationships. And this is one of the things that may influence our ability to develop principles. Go through one more slide here. This slide shows a relationship between biomass and time to 50% germination. So the number of days it took at 4 degrees Celsius for these seeds to germinate. And Stuart, don't kill me on this, because this is a very, very rough way to do this, and Stuart has much better ways to do it. But the point being is that our squirrel tails here are native grasses versus our annual grass populations take a lot longer to germinate. And in fact, we looked at both Medusa-head, which is this red dot, and Medusa-head from its invaded range, the western United States, red dot, and Medusa-head from its native range in the Middle East, comparing these populations. And we see both within populations, or within species and across species, that there's a pretty tight relationship between time to germination and how big you're actually getting. So what I want to point out here, I'll skip that, is that, back to this last thing here. So it's this last principle. So we have these low nutrient environments that are supposed to favor perennials over our invasive annual grasses. What we're looking at for this last principle is that we really have to manage priority effects through time, again, to have these low nutrient systems favor our perennials. Eventually, if we can do that, we might expect our perennials to actually be favored through time and our invasive disfavored. And one of the main mechanisms has to do, again, with the specific leaf area, where through time, our perennials are going to have much longer tissue lifespans and probably be more well defended against biotic and abiotic stresses. So that's kind of the way that third principle sets out. So just to wrap things up, we went through quite a lot of data that was looking at different principles here. But what we're trying to broadly do is develop this EBIPM model and understand how we can actually link the tools that we might apply in restoration with the processes that we actually want to modify. And the main way that we're going to actually successfully link these has to do with our understanding of the principles of liquidity. So, it's a pretty complex topic. There are some publications in the back where it's a little more explicitly laid out. But really, the closing point is, if we're going to be able to apply the tools successfully, we need to understand the conditions in which these principles hold. So, that's all. Thank you.